Chapter 7 is on application of definite integrals. Section 1 is on integrals net change. We've really looked at a lot of this stuff. It's going to be just a little bit different in terms of how it's presented, but it's really the same type problem that we've looked at a number of times. Example number 1, the function v of t. Typically in these problems, we're going to give you a velocity function. It's in meters per second of a particle moving along the x-axis. Use analytic methods. That means don't just put it in your calculator, although I'm going to show you how to do this in your calculator as well. It's a great way to check to make sure that your answer is right, particularly if you know the difference between net displacement and total distance traveled. This is where it really ties in. I've been stressing it because I knew this was coming up, but now is when you really have to know the difference between those two, okay? So the first thing we're going to do is determine when the particle is moving to the right, to the left, and stopped. In order to do that, we simply have to set the velocity equals 0 and check to see when the velocity is positive, when it's negative. So that right is going to get a little smaller here, but here it is. So in order to do part A, we simply set the velocity function equal to 0. Okay? If we divide both sides by 5, we really want to find out when does the cosine equal 0. If you're still unsure of when the cosine equals 0, draw yourself the unit circle. Cosine equals 0 when the x-coordinate equals 0. That will be this point right here and right here. That's the point 0, 1, 0, negative 1. Remember, cosine equals the x-coordinate. So we're looking at, this thing is momentarily at rest. When t equals pi over 2, and when t equals 3 pi over 2. Because that's when the velocity equals 0. A particle is going to be moving to the right and to the left, depending on when the velocity is positive or negative. So we draw our velocity sign chart, labeling the sign chart. We're only going from 0 to 2 pi. So we'll put that at the end, because this is a periodic function. It goes on forever. And then we're going to label our critical points. Here's pi over 2. And here's 3 pi over 2. It shouldn't be hard to check the signs here. If you pick a first quadrant angle, the cosine is positive in the first quadrant because all students take calculus. Everything's positive in the first quadrant. This is going to be positive. In the second and the third quadrants, the cosine now is negative because the x-coordinate is negative. And then in the fourth quadrant, the cosine comes back to being positive. So we know this function is going to be moving to the right. From 0 to pi over 2. In union with 3 pi over 2 to 2 pi. It's going to be moving left from pi over 2 to 3 pi over 2. Questions on part A of this problem? I know this might get a little small here, but to make it fit. The particle's displacement then. In order to find the particle's displacement, the displacement is equal to the value of the what? The what? The value of the definite integral over this entire interval. So for part B of this, we just want to evaluate the definite integral from 0 to 2 pi of this particular function. There it is. That's going to represent it. I'll show you how to do it on the graphing calculator when we're done here. To do it analytically, we need to take the antiderivative. The antiderivative of cosine is what? Sine. and we're going to evaluate that from 2 pi to 0. And watch what happens. We get the sine of 2 pi minus the sine of 0. What's the sine of 2 pi? 0. What's the sine of 0? 0. So we get a net displacement of 0. How can that be? Well, it simply means that wherever this particle started, it's going to stop at that same spot when it's done moving. And that's why we get a different value than when we find the total distance traveled. But in order to find the total distance traveled, I wish I could make this thing wider. Okay? In order to find the total distance traveled, I'll set up the integral here and then I'll work it out on the board for you. You have to set up the separate definite integrals. So it's going to be the definite integral from 0 to pi over 2 of this function, of the velocity function. We have to subtract the definite integral from pi over 2 to 3 pi over 2 of this integral. And then we have to add in the definite integral from 3 pi over 2 to 2 pi of this integral. We'll work out all the detail on the side here quickly. Before I do that then, on the side board, since you won't be able to see it if you come back and look at this lesson, all right, before we do that, let's take a look on the calculator then, how we can do this particular problem on the calculator to see if we have that right, okay? All right. So if we go y equals here, and we want to put in the function that we were just looking at, which is 5 cosine of x. Remember, this is the velocity function. They're giving us the velocity function. So let's start by checking to see if our definite integral is correct. So go second quit. Notice up here it's also showing you the steps, the actual buttons that I'm pushing. So when you come back and look at this online, if you struggle with it, the actual buttons will be on there as well. Okay? So we're going math 9 for FNINT. We're going to call, this is going to use this method. So it's going to go, it wants the lower bound. We're going from 0, okay, to 2 pi. Okay. We're going to call up the y1 function. Hopefully it'll let us do this here. I'm not sure. Maybe we got to type it in. Hopefully it'll let us go vars, O to y vars, function, y1. Okay. And this is going to be with respect to x. Got to put a dx in there. Okay. Hit enter. And it gives us 4.398 e to the negative 13. Well, what's e to the negative 13 mean? 0. It's the same as 0. Okay, so we're good. Now, the reason why I'm going to show you this on the calculator is I want to make sure that you know we can do this with one definite integral. Remember, if you're finding total distance traveled on the calculator, it really means the same thing as being able, I wish it would let me write here. Oh, it does. It's the same thing as if we can find the definite integral over the entire interval, but what do we got to do to the function? Put absolute value bars around it. If this is a calculator problem on the AP test, this is all you need to write, and then use your calculator to find it. They have been putting them on the calculator portion more recently. If they're not on the calculator portion, then you have to break it down into separate definite integrals like I was doing on the previous page. Does that make sense? You got to break it up. When is it above the x-axis? When's it below? I don't know whether it's going to be on the calculator or non-calculator. You have to be prepared for both. But watch what happens here. We can do the exact same way. So we're going to go Math 9 for FNINT. Clear this out. Math 9 for FNINT. Why is it not doing it? Clear? What's that? Yeah, but it's not. How do I right click it? There we go. Does that work? Math. Math 9 for FNINT. And we could just call it back up and put absolute value bars around it. We're going to go from 0 to 2 pi. Okay? We're going to call it the y1 function. Vars. O to y bars. Function. y1. And then we do have to put the dx in here when it's in this form here. So you got to put an x. Okay? Now, I got to go back. I'm going to put absolute value bars around this. Right? So I'm going to go math over the number 1 for ABS. Then I'm going to call it the y1 function. Okay? And now we get a value of 20. Okay? So that's the total distance traveled. Since they let me do it right here, I'm going to do the work right here. Hopefully there's enough room where we can see this and see if we actually get the same value if we crank this all out. In other words, if I take the definite integral from 0 to pi over 2 of 5 cosine of t dt and subtract pi over 2 to 3 pi over 2 of 5 cosine of t dt, and then add 3 pi over 2 to 2 pi of 5 cosine of t dt. Okay? If we anti-differentiate, we said we're going to get 5 sine of t from pi over 2 to 0. 5 sine of t from 3 pi over 2 to pi over 2. And then 5 cosine of t from 3 pi over 2 to 2 pi. And the key here is that all of the sines, go ahead. Oh, sine. All of the sines will end up working out here. So we're going to get 5 sine of pi over 2 minus 5 sine of 0. We're going to subtract 5 sine of 3 pi over 2 minus 5 sine of pi over 2 plus 5 sine of 2 pi minus 5 sine of 3 pi over 2. Okay? And I know this is terrible. This is probably the reason why I don't record too many lessons, because it's hard to fit everything on the screen. So here it is on the side. 5 times the sine of pi over 2. That's going to be 0. 5 sine of 0. Okay? Sine of 0 is going to be 1. Okay? Let me do that again. 5 times the sine of pi over 2 is 5. 5 times the sine of 0 is going to be 0. Subtract. 5 times the sine of 3 pi over 2 is going to be 5 times negative 1. Okay? Minus 5 times the sine of pi over 2. The sine of pi over 2 is positive 1. And then we're adding 5 times the sine at 2 pi, which is 0. Subtract 5 times the sine at 3 pi over 2, which is negative 1. So you get a 5. Subtract negative 5 and negative 5 is negative 10. and then you're going to add a positive 5. So this particle moves forward 5 units, then moves backwards 10 units, then moves forward 5 units for a total of 20 units traveled. And I see how we get that value. Everybody good? Let's take a look at the next example like this. Okay? What happened to my nothing? What's that? All right. Okay, let's do this problem now. It's the same idea. The only difference is the type of integration that we're going to have to use. So essentially, to do part A, we're doing the same thing. When does the velocity equal 0? The velocity equals 0. When we look at this, again, they love these e raised to functions on the AP test because they just muddy the water a little bit. They really don't have a huge impact because this is going to be the exact same thing. When does the cosine of t equal 0? And it's going to be the same 2 points. Okay? So at this point, it's going to be when t equals pi over 2 and when t equals 3 pi over 2. So the velocity function, written as a sign chart, here's 0, here's 2 pi. Here's 3 pi over 2. And here's pi over 2. And here's 3 pi over 2. Between 0 and pi over 2, it's the first quadrant. This is always positive. E to the sine of t is always going to be positive. The cosine is going to be positive in the first quadrant. So again, it's positive, negative, positive. There's no change between this and the first example in terms of the velocity situation. Okay? So it's going to be at rest when t equals pi over 2 and when t equals 3 pi over 2. It's going to be moving right from 0 to pi over 2 in union with 3 pi over 2 to 2 pi. It's moving left from pi over 2 to 3 pi over 2. Okay? Total distance traveled versus net displacement. That's really what this a lot of this lesson is about. So for part B, to find the net displacement, it's just going to be the definite integral from 0 to 2 pi of this function. That's it. Yes. Probably, in terms of moving to the right, moving to the left, you could certainly bracket here. You could put some brackets. The brackets versus parentheses is not going to be a huge emphasis on the AP test. Okay? But you could bracket at least the pi over 2 and the 3 pi over 2. Okay? When we're trying to find this particular integral here, the key is it's set up for a U substitution. But this is a great example of a problem where I'm hoping you don't have to walk through the U substitution process. How many people, raise your hand if you know what the antiderivative is right now? Well, that's it. Make a good guess, differentiate that guess, see if you can come up with it. Only 4 or 5? How many people got it now? Maybe. All right. Well, here it is then. I'm going to make u equal the sine of t. Why are we going to make u equal the sine of t? because something else is being done to it. It's being e raised to. But more importantly, the derivative sine of t is cosine of t. So now I can change this to b. I might as well change my bounds in. If I'm going to go forward with the u substitution, I might as well change the bounds as well. Okay? So I'm going to go, if I plug 0 in, the sine of 0 is 0. If I plug 2 pi in, the sine of 2 pi is 0. So right away, we know the net displacement here is going to be 0 as well. The key is to break it up. The next part is going to look like this. For part C, again, you would have to break it up into 3 separate definite integrals if you were to do this analytically. You would say, I'm going to go from 0 to pi over 2 of this function. We're going to subtract from pi over 2 to 3 pi over 2 of this function. And then we're going to add from 3 pi over 2 to 2 pi of this function. And you can crank that work out. I'm going to do it separately on the board here so that you can actually see it. Again, if you want to do a u substitution, you can do that in all 3 cases here. U is going to equal the sine of t, so that du equals cosine of t dt. We might as well change the bounds of everything as we go, though. So I'm going to go definite integral from 0. If I plug pi over 2 into here, the sine at pi over 2 is 1 of e to the u du. Then we're going to subtract. If you plug pi over 2 in, you get 1. If you plug 3 pi over 2 in, you get negative 1 of e to the u du. And then we're going to add. 3 pi over 2 is negative 1. 2 pi is 0 of e to the u du. But I'm hoping that people could just, the antiderivative thing, by the way, is just e to the sine of t, right? You can make a good guess there, not have to change it doing a u substitution. Don't forget, though, if you plug this in, you're going to get e to the first power minus e to the 0. E to the 0 gives us a number. Subtract e to the negative first power minus e to the first power. If you wanted, you could have changed this and made this a plus, or just evaluate it the way it is. Subtract e to the 0 minus e to the negative 1. Yep. And so you get e minus 1. Subtract, this is 1 over e. Distribute, that's e. That's a 1. Don't forget that that's 1. Minus 1 over e. So, the 1's cancel. E and e is 2e minus 2 over e is what we get for an answer. So when you calculate this all out, you should get 2 minus 2 over e. 2e. Okay. Let's come back, take a look at it on the calculator, see if we get those same values. Everybody got this? All right. Y equals. We're going to make this, the original function again was e raised to the sine of t times the cosine of t, correct? Is that what it was? Second e raised to the sine of x. I'm just going to use x. You got a cursor to the right then. Cursor to the right. Now we're going to have cosine of x. All right. So there's the function. If we're just doing the definite integral part, let's make sure it's 0. So I can quit. We're going to go math 9 for FNINT. We're going to go from 0 to 2 pi. To 2 pi. It doesn't like that pi key for some reason. All right. Oh, that's great. Figure that out. All right. 2 pi. There we go. All right. Now I got to call up the y1 function, vars. O to y vars.
Don't call it up, please.
What? Vars. O to y vars. Function. Y1. There's the x. Hopefully it's the 0. 0. Okay? Now, if we want, we do the exact same thing, but we put absolute value bars around it, we should get this value. Let's check it. 2 e subtract. That's fine. 2 divided by e. Okay? That's what we get for value right there. Okay? Let's see if we get that same thing if we put absolute value bars around this. So we can do this. Second enter. Second enter. It's going to call this up. The only thing you want to do is come back here and put absolute value bars in there. Okay? We're going to go math over the number 1. Now I'm going to call up vars, O to y vars, function, y1. Hit enter. And we get the same number. Okay? So it's the same thing as if you put absolute value bars around it. Okay? Questions on that? I want to make sure that you understand total distance traveled is the absolute value of it. Okay? Alright, here we go. Example number 2. Recall that acceleration due to Earth's gravity is 32 feet per second squared. From ground level, a projectile is fired straight upward with a velocity of 90 feet per second. So that means that the initial velocity at time 0 is 90. Okay? We also know that the acceleration is 32 feet per second squared. So what's the velocity after 3 seconds? To get back to the velocity function from an acceleration, we need to take the antiderivative. So when we look at this situation, it's going to be the antiderivative of 32, which is 32t plus an arbitrary constant. They're telling us that when you put 0 in for time, you get 90 out for the velocity. So that means this arbitrary constant here is going to be 90. So the velocity function is going to be 32t plus 90. That's part A. Now it wants to know what's the velocity after 3 seconds. The velocity in 3 seconds is going to be 32 times 3 plus 90. So that's 96 plus 90. Except this is probably supposed to be negative, right? Okay. So this is negative because the acceleration due to Earth's gravity, which is negative, which makes that negative, which means that the velocity at time 3 is negative 96 plus 90, or negative 6 feet per second squared, or feet per second. It's velocity, feet per second. That's the velocity at time 3. Okay, questions on that one? When does it hit the ground? Well, it's going to hit the ground when the position is 0. So we need to figure out the position function. And it tells us, though, that from ground level, so the position at time 0 is what? 0. So if we want to get back to the position function, to get back to the position function, we have to integrate the velocity function. So the position function will be the integral of negative 32t plus 90. If we anti-differentiate here, t squared over 2 makes this negative 16t squared plus 90t plus an arbitrary constant. We know that the position at time 0 is 0, so the arbitrary constant is what? 0. So here's the position function. Okay, negative 16t squared plus 90t. It hits the ground when the position equals 0. So if we plug 0 in for the position, what is the time going to be? Factor out a time, a t. You could factor out more than that if you wanted. There it is. It's certainly not going to be when t equals 0. That's when it starts. But we set this equal to 0. Add the 16t to the other side. So you get 90 equals 16t. Divide both sides by 16. If you reduce by 2, you're going to get 45 over 8. And you can figure out that that's 5 5/8 seconds is when it's going to hit the ground. Okay? When it hits the ground, what's the total distance that it's traveled versus what's the net distance it's traveled? Well, the net distance it's traveled is going to be what? 0, right? It started on the ground and hit the ground. This is just going to be 0. The definite integral of this position function, okay, of the velocity function, the definite integral of the velocity function over this entire time, here's how you can write the definite integral. From 0 to 45/8 of this velocity function is going to be 0. Versus the total distance traveled. The total distance traveled is going to be the definite integral over this entire time, but we have to take the absolute value of this function. Okay. We'll just do this one in the calculator. We won't break it up separately. But you'd have to break it up to find out where the maximum point is, and break it up if you had to do it analytically. But to do it in the calculator, is everybody at this? Wait a second. We'll pull up the calculator and do it in the calculator. that good? We got it? Okay. Y is going to equal negative 32t, or x in this case, it really doesn't make a difference, plus 90, is that what it was? Is that right? The key is, when we do this, we're going to go math 9 for FNINT. Math 9 for FNINT. We're going to go from 0 to 45/8. But we have to take the absolute value of this. Math over the number 1 for ABS. Then call up the Y1 function. Put an X there. And we get 253 1/8 units. How many people had? Everybody get that? 253 1/8. Okay. There it is. Questions on that problem? To break it up, you can look at this analytically and break it up between 0 and be 45/16. Okay, when it's going up and when it's going down, if you had to do it analytically without the absolute value bars. All right? Last problem. The rate of consumption of oil in the United States during the 1980s in billions of barrels per year is modeled by this function, where T is the number of years after January 1st, 1980. Find the total consumption of oil in the United States from January 1st, 1980 to January 1st of 1990. This is very typical of a type of application problem that they might put on the multiple choice section. Do you recognize then that this is just an integration problem? That's all it is. This is a definite integral that we have to find. We can accumulate anything. A lot of times we accumulate distance, but we can accumulate, in this case, is oil consumption. But anytime you want to accumulate something, that means integration. Integration is an accumulator. So we want to accumulate from 0 to 10 of this function. There it is. On a problem like this, it more than likely will appear on the calculator portion, but you never know. Again, hopefully we don't have to use a U substitution to do this. I would start by guessing this is e to the t over 25. But if I take the derivative of this, I get e raised to the t over 25 times 1 over 25. I don't want that times 1 over 25. So what do I do? Multiply by 25. I've already got a 27.08 out front. So 27.08 times 25. Anybody tell me what that number is? 600 and what? Exactly. Okay, 677. And we're evaluating this from 10 to 0. If we plug in 10, we get 677. E to the 10 over 25 minus e to the 0. Don't forget that that's 1. This is 2/5. So it's 677 times e to the 2/5 minus 1. Okay? You can leave your answer like this. But since it's a decimal, you know, it's a problem like this, we probably want to give the decimal answer as well. But if we had to use our calculator, we could have just done, you know, the definite integral of it. So 677 times e raised to the 2/5 okay, and then we're subtracting 1. Is that what it was? 332.965. 332.965. Okay, and make sure that this says this is the rate of consumption of oil in billions of barrels. So billions of barrels. But the main reason that I gave you this example is so that you recognize we can accumulate anything. Oil, sand coming on a beach, sand coming off a beach, whatever it might be. But when you're accumulating something, it's integration. All right? Here's the assignment. It's in your notes. Everybody good?